Welcome to Pi Art Tuition, a series of mini tutorials to help you get more out of your creativity when drawing and painting. In this second video, we're going to continue looking at primary colours. In the previous video, we looked at what are the three usual primary colours. What actually is a primary colour? In this video, we'll be explaining why are there two sets of primary colours? And what exactly is the second set of primary colours? First, a quick recap of what we covered in the previous video. In the previous video, we concentrated on the primary colours of pigments. We said that the primary colours were not in fact red, yellow and blue, as many of us were taught when we were young. Instead of red, we have magenta. Yellow is correct, it is a primary colour. And instead of blue, we have cyan. We also said that you can prove this for yourself if you happen to own a computer inkjet printer, because the inkjet cartridges will be these same three colours: magenta, yellow and cyan. And these three colours can combine to make any other colour. We also mentioned that the black cartridge is also used when printing colour photos to increase the contrast of the image, in other words, to produce darker shadows. And we mentioned that magenta is not the same as red, and cyan is not the same as blue. Cyan and blue are different wavelengths in the visible spectrum, or they're at different positions in the rainbow, if you like. Cyan is not simply light blue. We obtain light blue by adding white pigment, or by illuminating a blue object with a stronger light. Artists and scientists call the colours in different parts of the spectrum hues. So that's a quick recap of what we covered in the first video. In this video, we're going to look at why are there two sets of primary colours, and what are the primary colours of this second set? Remember, the primary colours of pigments are magenta, yellow and cyan. But don't forget, this applies to pigments. Let me explain why that distinction is so important. So far, we've been talking about primary colours which relate to light reflected off a coloured object, for example, the pigment in your paint. White light from the sun contains all the colours of the rainbow, which artists and scientists call hues. Each pigment absorbs all the colours except its own colour, which it reflects. So the yellow pigment absorbs all the colours of light except yellow, which it reflects. Similarly, the blue pigment absorbs all the colours of light except blue, which it reflects. Now I'm only mentioning the pure colours of the spectrum here. The same principle applies to all the millions of different shades, tints and tones of colours we see around us. Dark green, chocolate brown, light brown, medium grey, rose pink, even gold. You name it, the principle is the same. It's just that in most cases we're seeing a combination of wavelengths of light, or hues, reflected off objects. And these wavelengths of light are often at various intensities, which also affects how the colours look to us. I'll be covering this principle of how the millions of colours which we see are created in the next video. Now, before we talk about the second set of primary colours, it's important to remember that the more various pigments are mixed together, the darker the resulting colour becomes. This is why pigments are known as subtractive colours, because each additional colour subtracts more light, until finally there's hardly any colour reflected at all, and the object looks dark grey or black. So 99% of everything we see around us absorbs certain colours of the spectrum and reflects the remainder. The colour or colours it reflects are the colours we see when looking at the object. The exception is objects which emit light, such as a laptop screen. So now let's look at the primary colours of light-emitting devices, and these are the second set of primary colours. The second set of primary colours belongs to light-emitting objects such as your laptop, mobile smartphone, TV, computer projector, etc. These screens don't absorb light, instead they emit light. This is known as additive colour. And although it looks like the screen is showing full colour images, in fact it's only projecting 3 colours, the primary colours of additive colour devices. Red light and green light, when combined, create yellow light. Green light and blue light create cyan light. And red, green and blue light, when combined in equal proportions, create white light. Unlike pigments, which subtract more light and get darker, the more different colours are mixed together with devices which emit light, the projected colours add together and the resulting image becomes brighter. So white is produced when all 3 primary colours at full intensity are emitted by the screen. And if we look at a close-up of the screen, we'll see that each pixel is comprised of 3 coloured dots or bars, each emitting red, green or blue light. And black is achieved by simply switching off the coloured bars creating each pixel so that no light is being emitted. When you see black, you're actually looking at the natural colour of the screen when the device is switched off. Oh, and by the way, the screen is often dark grey, not black. When the device is switched on, the black areas of an image only look black because the grey screen looks very dark compared to the bright colours on the projected image. Now you may not be totally convinced that when you look at your smartphone or computer screen or TV, that the full colour image that you're seeing is actually being produced by just 3 colours of tiny light-emitting dots or bars spread over the screen. Well, this is a photo I took of my computer screen. Let's zoom in to look at that yellow letter O in more detail. And a bit more. And a bit more. And let's turn the brightness down a bit. Now we can see that the area which appeared white is actually made up of lots of tiny coloured bars emitting red, green and blue light. And the letter O, which appeared yellow, is actually made up of just tiny red and green bars, and the blue bars have been switched off. So I hope that proves that when we're looking at light-emitting devices, such as a smartphone, or a computer screen, or a TV, the full colour image we see is produced by just red, green and blue light-emitting dots or bars spread over the screen. If you happen to have any video equipment which handles analog signals, you may have noticed that there are sometimes sockets marked red, green and blue for this very reason. The electrical signals carrying red, green and blue information are sometimes conveyed in separate cables in order to improve picture quality. Similarly, if you have an old VGA or SCART video cable, the red, green and blue signals will be conveyed to different pins within the multi-core connector. Well, that's all we're going to cover on the primary colours of light-emitting devices. In the third and final video in this series on primary colours, we're going to return to looking at the primary colours of pigments. In the next video, we'll be looking at the primary colours of pigments in more detail, including How do the pure hues of the rainbow produce the millions of different colours we see around us? When mixing two primary colours to give a third colour, is it our eyes or our brain which generates the third colour? And does the colour magenta exist in reality? These and many more groundbreaking topics will be discussed in the next thrilling instalment of
Pine Art Tuition.